Well, welcome everyone. I'm delighted to see such an interesting geographical turnout with listeners from Orkney to Fife, from Edinburgh to Forres, and with our speaker, Dr. Stewart Redwood in Panama. Stewart lives in Panama, works there, or maybe I should say he's based there because Stewart's work as an independent geological consultant specializing in minerals exploitation, his work carries him to many countries. Over the years, he's visited more than 60 countries, and that's included crossing both polar circles. Stewart's background is in Scotland with a geology degree from Glasgow University and a PhD from Aberdeen. The issue he's going to talk about is where geology meets energy and both converge on questions of the future. We hear a lot about net zero, and just about everyone will say, yes, it's a great thing to do, but the question is, how do we accomplish it? Turns out that to build advanced renewable energy systems and to develop electric cars means a huge amount of metals that are not always easy to get, ranging from copper to cobalt and nickel to lithium. Well, that's Stewart's field of expertise. And Stewart, it's now over to you to highlight some of the questions and hopefully give us some of the answers.
Thank you very much for the introduction, Howie, and good evening, everybody. Thank you for listening in. The subject of tonight's talk is the subject of net zero or the green energy revolution, and the dilemma of where will all the metals come from. It will require a lot of metals, and in many cases they are critical minerals, critical metals, and in many cases it will require an increase on what's currently produced, in some cases many times. This photograph on the front is the world's biggest copper mine in Chile, Escondida. The annual output of that could produce enough for 18 million electric cars. That's a lot short of the total that's needed. I've put Scotland in the title because RUI is a Scottish institute, but I've put this slide up to remind us it's really a global problem. If it was just Scotland, it wouldn't be an issue, but many countries have signed up to the net zero. So we need to look at this from a global perspective of mineral supply and demand. And I don't know if people recognize this photo. It's actually, it's a real photograph. It's actually the Tesla Roadster launched into space as a cargo on a test mission a couple of years ago. And it reminds us that in electric cars, this, for example, takes 180 pounds of copper. That's almost 10 times what goes into a normal petrol-powered car. So where will the metals come from, and is net zero feasible in the timescale envisaged, or is the extra demand of metals achievable? Now, this is put up to remind us this is not the first time the world has been through an energy transition. There's been several over the last 200 years. The original energy sources were biomass, in other words, wood and dung, and using wind and water and animals and muscle power. Until about the mid-19th century, then coal became the principal source of power, together with technological, in other words, invention of the steam engine, the external combustion engine. And although oil was discovered about the same time, oil didn't become important till into the 20th century, and then later into about 1960 that gas replaced it as the dominant fuel for heating and electricity. And we see at the current and in the late 20th century some nuclear and now an increasing amount of renewables from the last 10 years or so. So the fact that we've been through a number of changes is not new. That's the speed with which it will be done, and the fact that it's not so much driven by technology, new technology, as by environmental reasons. So what's required it basically means change over to electrical energy from fossil fuels, and to produce sources of clean electricity. That means changing vehicle fleets to electric vehicles or possibly hydrogen-powered vehicles, changing electricity generation to clean and sustainable energy, and that requires battery storage as well. So there's a large amount of both infrastructure and required, a lot more electricity generation, and consumer goods, let's call them vehicles. And this requires a whole variety of metals, including lithium, cobalt for batteries, graphite for batteries, nickel, rare earth minerals, rare earth elements, copper, manganese, aluminium, platinum group metals. And we'll talk about these in a bit more detail. A lot of these, I want to introduce the concept of critical raw materials. A lot of these metals and materials are defined as critical raw materials by the European Commission. They've published, their last list was published 2 years ago. It has 30 minerals, and they're defined as minerals that there is no domestic supply in Europe, complete reliance on imports, so there's concern over secure and adequate supplies. They're minerals that have essential uses, and there's potential for supply disruption. And recent world events of the lockdown and the pandemic have highlighted that supply chains are actually very fragile. You close down a port in China because the workers have COVID for a few weeks. The knock-on effect is it ripples all around the world. Ships get backed up, containers get backed up, goods don't get delivered, goods don't get picked up. Shipping schedules get completely out of sync, and that's causing chaos in supply chains. Plus, the Ukraine war has shown that it's not a critical raw material, but it's a critical supply of natural gas to much of Europe has been cut off by sanctions. And now we're realizing that the supply of a lot of the wheat has grown in Ukraine, and it's now the ports are blockaded. So there's already been a realization, and that's been brought home with recent world events, that there's a big risk in materials supplied from other parts of the world. And then the list is on the right. I won't go through it all, but it includes things like cobalt, things that we mentioned, the rare earths, graphite, rubber, platinum, tungsten, lithium, and so on. This map goes with the EU study. It shows, it's quite surprising, it shows the countries where the EU gets critical raw materials from, and it covers a large part of the world, particularly Asia, the Americas, and some parts of Africa and Australia. Now the US also has a list. They've actually been worrying about this for longer. It's maintained by the United States Geological Survey. They have 50 minerals on it, but they list all the rare earths individually and the platinum group metals individually, so it's a similar number. And they have the Energy Act defines a critical mineral as a non-fuel mineral or mineral material essential to the economic or national security of the US, and which is a supply chain vulnerable to disruption, which is exactly what we're seeing now. And critical minerals are also characterized as serving an essential function in the manufacturing of a product, the absence of which would have significant consequences for the economy or national security. And we see the US minerals list. I won't read through that, but it's put in order of criticality. The UK surprisingly does not have a list, an official list. The British Geological Survey has information on its web pages about it, and they've done a lot of research on it. But they refer you to the EU's list when you click on a list of critical minerals. Rather surprising that the UK doesn't have its own list, because it has the same issues. And similarly, a map by the US showing the US's dependence on critical minerals. So all of the Americas, Asia, Kazakhstan, and then some parts of Europe and Africa, particularly dependent on Asia. And we'll see in particular China rare earths. China dominates the rare earths production and market. That's a similar map shown by the darker the colours, the more commodities from the countries. So Canada, obviously, that's a good neighbour, but China and Russia stand out as big suppliers of critical minerals to the US, which is obviously Russia situation has changed completely since this was drawn up, and China's a concern as well. Now there are different the change in demand. This is one example from a couple of, well, it's 4 years old actually, and there are different estimates, but we see the current levels are taken as zero. And we see the most extreme is lithium with a 2,000% predicted increase. That's a 20 times increase. Cobalt's almost the same. Cobalt's a tricky one because cobalt's a byproduct. It's almost no primary cobalt mines. Rare earths, again, a 6 or 7 times increase. Graphite, a very large increase. You would think graphite it's a pretty common mineral, but I've worked in graphite projects, and the actual specifications for battery graphite are very high in terms of the type of crystals and so on. It's not just any old graphite. Nickel, more modest, but it's still a doubling of supply. Copper, manganese, aluminium. Strangely enough, this has a decrease in platinum, but platinum's essential for hydrogen catalytic fuel cells, so they require that. We'll look at the number of the metals one by one. These are a number of charts showing the number of discoveries of copper per year over the last century, and copper comes from two main types of deposits: porphyry copper deposits, which are big disseminated deposits, mainly Chile, Peru are the main sources, and then sediment hosted copper deposits, which are generally flat lying, hosted in sedimentary rocks. They come from the Zambian copper belt in Africa and from the Zechstein in Poland. And then another class that's called iron oxide copper gold, which occur in Australia and Chile and so on. And one of the things to notice on the discovery chart, this is by contained copper, 200 million tons. It's dominated by a few supergiant deposits. There's a lot of regular ones in the 20 to 50 million ton mark, which is a lot. And then there's a few giant ones, almost all in Chile, El Teniente, Chuquicamata, more recently Escondida, which was the first photo that I showed. So those super giant deposits are rare. There's maybe 10 shown here, but they produce an extraordinary large amount of the world's copper. Now you'll see it's in the last decade, it's tailing off a bit without accounting for even the demand. This is the predicted demand, and this graph was made in 2017, so it's 5 years old before the net zero was really adopted, so that the actual forecast demand is higher. The point of this is over the next 30 years, the amount of copper required is as much as has ever been produced in all of history, in the order of 700 million tons. So that's got to be, a lot of that's still got to be found, and that's the challenge for exploration and for mining. A reminder that the amount of copper convention, this is showing on the relative amounts in conventional car in yellow, uses 18 to 50 pounds of copper per car. Battery electric vehicles, electric cars, contain up to 180 pounds of copper, and then an electric bus, for example, 800 pounds of copper. So a lot more copper is going to be needed, or is needed, in electric vehicles than at present. And the batteries weigh a lot. I think the battery in a Tesla weighs half a ton or something. So you're also expending energy, electricity to move that around, as well as the payload, the passengers and the suitcases, rather than just a tank of gas. So there's a Tesla Model S, takes 180 pounds of copper. And the other thing we don't always remember is the infrastructure. This picture is a cross section of a submarine cable that connects offshore wind farms. That contains 50 kilograms of copper per meter. The three cables, I don't know if you can see the mouse when I move it, the three cables, core cables, are full of copper. So that's a mass amount of copper, that big diameter cable. Nickel occurs in two types of deposits: nickel sulfides, which occur on mafic and ultramafic rocks, and nickel laterites, which are formed at the Earth's surface by weathering. So it converts nickel, low-grade nickel that's in rock minerals like olivine, and forms laterites. But although they're at the surface, they're actually harder to process. They're more complicated to process. And we see in this chart over the last century the big surge in the post-war years. A lot of the biggest deposits were found in the 70s, 60s, 70s, and then some more modest in the 2000s, but generally showing a decrease as well. So there's a shortage of nickel. Cobalt goes with nickel. It's produced, almost all cobalt as a byproduct of nickel. It's associated with, in both types of deposits. In dark green, there's one or two primary deposits of nickel, but there are very few, less than 5% of the total are primary deposits. So if you recall from one of the first purchases, the demand for cobalt is many times higher than present, and it's difficult to see how you do that when it comes as a byproduct. You're not needing nearly so much nickel. Lithium, that's the battery metal. The traditional source are pegmatites. Pegmatites are veins in granites, with the ones that form the coarse crystals, and you concentrate the rare metals like lithium. This is mineral, the spodumene. That's the principal mineral that's extracted from pegmatites and is processed. And some of those can be very big, in particular Western Australia, can be tens of millions of tons. And the new resource are brines in the salt lakes. And you'll have heard of the so-called lithium triangle, which is Argentina, Bolivia, and Chile, that produces a large part of the world's lithium. And this photograph here is the salt crust on the Uyuni salt lake in Bolivia, which is the world's biggest salt lake and the world's biggest lithium resource. And the lithium is very soluble. So the lithium is in the brines beneath the surface. It's one of the last things to crystallize, or in most cases it doesn't crystallize. Other non-traditional resources of lithium are in clays. Some lacustrine clays contain lithium, and there are some big resources, but it's a new technology to extract that. And then lithium is actually quite a common mineral, but it's how to extract it. It occurs in oil field brines, for example. There's a lot of research on how to extract them from oil field brines, because that would help environmentally to clean up oil field brines, which are considered a hazardous waste just now and have to be treated. But the technology is not commercial yet. We'll move on to the rare earth elements. The rare earths are a group of 17 elements, of which China has a monopoly on 70% of the global exports, and the majority of the US supply comes from China. For example, there are 8 different rare earths in a smartphone, and they're used in electric vehicles, electronics, X-rays, color TVs, permanent magnets, for example, for wind generation. And the demand is predicted to rise at least double by 2030 or more. The graph on the left is a bit to the right, showing the percentage of different rare earths exported to different countries, Japan, the US, Korea, Netherlands, Italy, and the rest of the world. And you can see that it's the dominant supply for the majority of countries. And that's an issue. We can see here, this is a chart of production. China in red has dominated it. Australia's started producing a bit in recent years. The United States did produce, but it got closed down. And where does it occur? It occurs in unusual heavy minerals, bastnasite, monazite, xenotime, that's an example here. And some other minerals like apatite and so on, phosphates. And the types of deposits are carbonatites. Carbonatites are unusual deposits, igneous deposits full of carbonates rather than silicates. Ion absorbed clay rare earths, that's a new type. And then these minerals are heavy, so they concentrate in beach sands and placer deposits, and a small amount comes from granites. And again, showing production by country, that's similar to one of the previous graphs. Now, one of the reasons China is dominant is thanks to this mine called Bayan Obo in Inner Mongolia. This is a satellite image. This single deposit has 80% of China's reserves and 40% of the world reserves. So it's a huge concentration of rare earths in one place, and China has taken advantage of this geopolitically to control the market. And I think in 2010 it restricted exports and squeezed out other producers and sent prices up. And it's actually said as a political policy it will not hesitate to use rare earth supply for geopolitical ends. So you don't want to be so dependent on that. There is an opportunity though. This is 40% of world reserves, so it's not. There is an opportunity for other countries. The US has deposits in California. The rare earths are actually not so rare. The challenge is processing them and extracting them from these minerals. They occur together, and separating the different minerals is more the challenge in an economic fashion. Then we move on to the minerals. We move on to platinum group metals, which are essential for hydrogen fuel cells. They occur almost exclusively in layered mafic and ultramafic intrusions. This picture on the left is the Skaergaard intrusion in Greenland. They're beautiful rocks to work on. There's several of them in the northeast of Scotland and Aberdeenshire that I worked on for the British Geological Survey. And the actual minerals they look like sedimentary rocks, and they have sedimentary textures, very unusual. But there's only a few of them in the world. There's only one deposit in the United States called Stillwater. The main one is the Bushveld in South Africa, the famous Merensky Reef, which is a section on the right of the screen. The Merensky Reef is the actual concentration of platinum is just in the black layer here. It's only 10 or 20 centimeters thick, but it's incredibly rich. The Great Dyke in Zimbabwe is one of the other sources. There's a couple in Finland and Russia. The Skaergaard in Greenland has a resource that's not been exploited yet, but that's a potential resource in the European Union. Interestingly enough, this was studied for more than 50 years academically to study the processes in these types of intrusions, and it was not until the 1980s that we actually discovered platinum reefs meaning beds or layers within the intrusion. Now, other potential sources are, we'll look at new metal sources. First of all, new technology. That has the potential to developing new technologies to extract metals from ores. For example, in the technology of crushing and grinding, that uses a huge amount of energy. It's one of the highest costs in a mine, is to grind the rock fine enough so that the minerals are liberated and then can be concentrated. So if you could find a way to reduce that energy input, that would make mining a lot more economical and lower cutoff grades. Experiments, technologies being done with ultrasonics and other sonic methods of doing that. One of the other holy grails of metallurgical technology is to be able to leach copper sulfide ore. Just now, leaching is restricted to oxides, which are soluble in acid, and the actual sulfides don't leach well. So if you could leach sulfides, that would again reduce costs and make a lot more lower grades. Then there are other things such as processing copper arsenic ore. A lot of copper deposits in the Andes in particular, copper is in a mineral called energite, which is with arsenic. Now you can concentrate that, but nobody will buy it from you because of the arsenic. No smelter will touch it because the arsenic is an environmental problem. So you need to find a way to remove the arsenic into a stable product, such as an oxide mineral. And there are a number of laboratory pilot scale methods, but nothing yet has been put into a commercial scale. So when something becomes commercial, that will open up a lot of energite copper deposits for exploitation. And then I've mentioned briefly earlier technology to extract lithium from clays and oil-filled brines and so on. And there's a lot of lithium potentially available in those areas, and let's call it non-traditional sources. Recycling, we'll touch on this briefly. A lot of talk is of recycling and the ideal that recycling could achieve 100%. Problem is a lot of metals such as zinc and iron actually oxidize and rust or go away, so they're lost. A lot of other things like the rare earths and so on at the top here, they tend to go in telephones, televisions and so on, so they're dispersed in tiny amounts and mixtures, and billions of different small consumer objects that are scattered all over the world, and only a small percentage of them get recycled. Most of them end up in the back drawer when they stop being used. Other things like lead and bismuth are used, for example, in solder, and that's almost impossible to recover from circuit boards and electronics. So it's the ones that are higher recoveries. We start to look at platinum, metals, rhodium. They're more inert and more easy to recover. Tungsten, because it's a hard mineral. So there are efforts and work to improve recycling, but it's difficult to see it ever becoming 100%. In addition, we're looking at often metals get tied up, for example, in infrastructure for many decades or even hundreds of years, steel in buildings and aluminium and so on, copper wiring. So that's not available to recycle for a long time. Now we introduced a question here of peak metals. We've heard of peak oil, and there's been debates about whether peak oil is real or not. Is there an equivalent in peak metals? In general, this chart here shows most of the useful metals we would talk about by years of reserves. So most of the ones at the green is up to 500 years of reserves, blue 100, yellow 50. So some metals do have relatively low reserves, up to 20 years, including zinc, gold, surprisingly, lead, tin, antimony. Platinum group metals are I would have thought would go in there as well, because they are fairly limited supply. So there's some reserves, but remember, reserves is an economic term. It's what's been defined as actually mineable at a profit. Things like lead and zinc are very common in the Earth's crust, so and gold is quite abundant, or widespread, I should say, in small amounts. So increased exploration will keep up with that, and probably a similar graph or chart drawn 20 years ago would have probably shown a similar picture, so that exploration replaces reserves and keeps up. This is making a similar point. This is all the number of mineral deposits discovered per year over the last 200 years. And we see obviously there's peaks and troughs through the business cycles, but we see through basically from the 1950s, post World War II, a tremendous increase. So it's shown that metal exploration has been able to, and discovery has kept pace with demand. More than half of the metals ever discovered have been discovered since 1980, in the last 40 years. Now this chart shows a tail off in the last decade. Is that real, or is it a lag time in reporting and in realizing that the real size of new discoveries? That's an open question. Now I'd like to introduce the mining life cycle. So if we need more metals, but it takes, the point to make here is it takes time. The four main stages are, first of all, exploration and discovery, then the feasibility and construction, and that includes environmental impact statement, social and community license, government permitting, financing. Then you have the mining and extraction phase, and then finally mine closure and site rehabilitation and monitoring. And these are some examples from Arizona, from the source of this graph. Exploration and discovery can take 2 to 8 years. That's, I would say, a minimum. It can take a lot longer and cost anything up to 15 million. The feasibility and construction stages, so that's defining a deposit, drilling it out, doing all the permitting, social licensing, permitting, 4 to 12 years. Again, that's a minimum, and it can take, and construction can cost billions now. So you can see from this stage 1 and 2, you can easily be 20 years from starting to look for a mine until you get into production. So that's a long time frame, and a lot of mines are decades in planning, take a long time to permit. So it's not, you can't just turn on the tap and produce more metals tomorrow. It takes a long time. Mine life can be anything from a few years to typically 20 to 30 years, but some big mines have been in operation for more than hundreds of years. And the costs can be in the hundreds of millions per year to run and operate a mine. So you need to have good metals prices to operate those at a profit. And then the closure and rehabilitation obviously depends on the size of the operation and whether it was underground or open pit. But that can take several years, up to 10 years, and can cost many tens of millions. And the more advanced countries, the US, Canada, Australia, require an environmental bond to be posted so that the money is there to rehabilitate the mine if it closes. Other countries, in more third world countries, don't often do that. So if the mine closes or the company goes bankrupt, then you have a problem. Now the start of all this is the exploration business, and I've talked about this in the past and written a business paper about it. And it's important to emphasize that exploration is a business. It's not just a cost center for a major company that gets cut when budgets get cut. And I like to call it exploration and discovery, E&D. It's the research and development, the R&D of the mining industry. And interestingly, junior companies make 2/3 of the discoveries, as opposed to major companies and governments or major organizations such as United Nations. Junior companies being defined as companies with no revenue. In other words, they're entrepreneurial companies that are set up with the express purpose of exploration. So that shows how important innovation and entrepreneurship is. We won't have discussed this in the past, we won't go into it. Just to emphasize that this is since 1900, the makeup of companies that until about 2 decades ago, it was major companies accounted for the majority of discoveries. Now it's been taken over very much, replaced by junior companies. Now, the exploration challenge is where to look for more minerals. I'll show some slides following this, showing that discoveries are getting deeper and fewer. They're getting harder to make. In other words, the easy ones have been found, the ones that are outcropping mostly. So where to go? And I've got 4 suggestions or 4 recommendations here. The first is a return to domestic supply from UK and the EU. The recent world events have exposed the supply chain risk and the dependence on other countries that may be hostile or decide to cut supply chains, or when supply chains get disrupted, like with the COVID. The EU for the last 10 years has been concerned about this with the critical raw materials definitions, and there's actually a policy in Europe now to what they call a trend reversal, to look domestically again. Europe now supplies only 3% of global mining output by value, versus 40% a century ago. It was the dominant supplier in the world. And an additional benefit of this would be to create new sustainable domestic industries in the country rather than offshore. The next place is undercover at greater depths, and I'll show some graphs of this. Exploration is starting to look deeper in the more mature countries like Canada, Australia, where the outcropping stuff has been found. So covered, sometimes at considerable depths, 1,000, 2,000 meters. But this brings with it higher costs for exploration and mining, higher technical risk because it's harder. You're looking beneath cover, higher geological risk, but your trade-off is lower political risk. And obviously that means underground mines, and often underground bulk mining. For example, copper is quite commonly mined in large block caves, and that has a lower environmental impact than an open pit. So from that aspect, it is more socially and environmentally friendly. Having said that, there are still half of new gold discoveries are made at surface, and they're in new countries or new mineral belts that have been underexplored in the past. So you have lower geological risk, but you're balancing that against the higher political risk. I'm thinking of countries in the last 10, 20 years. Colombia, Ecuador, and the Guyanas have opened up, and been a lot of very good discoveries for gold and copper and so on in those countries. Now the Middle Eastern countries are starting to open up, Egypt and Saudi Arabia and so on, Pakistan. Those are countries that have never really been explored in the past. And then the final one that I think will be very important is deep sea mining. And I'll talk more about that in the last few slides. And the deep ocean is defined as the common heritage of mankind. That means it's administered by a UN body. It means that any country or company backed by a country can have access to it. So it can include landlocked countries, small countries, etc. So it doesn't, everybody has an equitable opportunity to share in it, rather than the shall we say, the luck of being a large country or a small country, or a country endowed with good mineral resources. And that is now several countries are now at trying out commercial mining with full-scale operations. So that will become commercial in the next 2 or 3 years, I think. As this is happening, the technical risk is being lowered, and it's building along a lot. So that's a quick table here of there's already, we're seeing an increase in UK domestic mining. Scotland now has a mining industry, a new mining industry in the Connaught gold mine in Tyne Drum. There are several other companies. Green Glen Minerals is exploring for gold in Loch Tay. A new company called Aberdeen Minerals is exploring in the northeast of Scotland for nickel, copper, cobalt, platinum. And then the other area that's been revived is Cornwall, with companies looking at reopening tin mines and tungsten mines, and some of those have copper, and also looking at lithium in the granites in Cornwall, and lithium in groundwater in the granites, and looking at innovative sources of lithium. So we're already seeing a renewed interest in domestic mining and exploration in the UK. And just a reminder that Ireland, the Republic of Ireland, has a major mining industry. This is Europe's largest zinc mine at Navan, not far north of Dublin. The mine is entirely underground. What you see on the surface is not much more than a big farm, and you'll notice that it's entirely surrounded by woodlands. That's deliberately planted as to mask it. So the visual impact of that is minimal, and it's, I think, the 8th largest zinc mine in the world. So why can't Britain, the UK, have rebuild a domestic mining industry? This is from the EU's critical raw materials. What this map is showing is the location, occurrences of all the mineral occurrences on the critical raw materials list. On UK is not shown, and I couldn't find a similar map for the UK. But the point is, the black dots showing there are a lot of potential sources in Europe of critical raw materials to be explored, and a map of the UK would show a similar pattern. And the next map, also from the EU, is showing battery raw materials as graphite, lithium, nickel, and byproduct cobalt. And it's showing, again, widespread occurrences in Europe. And interesting, it's showing in relation to current jobs in coal mining, particularly in Poland and Eastern Europe, and showing that it would go along, the areas often coincide, so it would help to replace jobs and industry in those areas as coal is phased out. Now, one of the problems is the quality of discoveries. Before even considering the increased demand in the last decade, the number of discoveries has been decreasing, and the quality has been decreasing. By quality, we mean the tier 1 and tier 2 deposits, which are the dark red and the red down here. They're only a small percentage in terms of number, 8% in number, but they represent 2/3 of the value of the mineral deposits found. So most of the value is in a small number of high quality deposits, and the number of discoveries is decreasing. That's a concern. And as we say, the easy deposits, this is gold discoveries over the last century at depth. So 0 is surface down to depth, and we see that the yellow is the world excluding South Africa, and we see that since the post-war exploration has been getting deeper, and some mines have been getting deeper, a general trend. The exception here is South Africa, where the exceptionally rich, right from the early 20th century, the mines started to go very deep on the very rich reefs on the Witwatersrand. They're a rather special case. The Witwatersrand alone is by far the single largest source of gold in the world. But there's a trend for going deeper to explore for gold deposits now. So that means that the easier ones have been found. And we see a similar trend for base metals, that's copper, nickel, zinc, and lead. And in fact, going even deeper, twice as deep, we're looking down towards 2,000 meters now, some of these deposits. So as I mentioned earlier, exploring that deep is costly. You've got to drill long holes. It's more risky because the technology, your exploration techniques don't work so well through all that cover rock or cover sediment. But it tends to be in more mature countries like Australia and Canada and the US, so your political risk is a lot lower. Now, the final few slides I want to look at deep sea mining. That's now at the stage of full-scale trial mining. It's probably 2 or 3 years away from commercial mining. And there are two main types of deposits. There are manganese nodules, which we see in the photo, which are manganese, but contain copper, nickel, cobalt, molybdenum, and they occur on the surface, about the size of potatoes, and carpet vast areas of the abyssal plains of the oceans. The other ones which I didn't list here are massive sulfide deposits at hydrothermal vents on ocean ridges. And the ownership of that, the individual countries have their own exclusive economic zones to 200 nautical miles limit. So for example, that covers all of the UK's oil and gas, or if it's not 200 nautical miles, then it's, for example, the North Sea is halfway to the neighbours. But beyond that, when you get out into the Atlantic or the Pacific, beyond 200 miles is called the International Seabed Area, and that's defined as the common heritage of mankind. And it's administered by the International Seabed Authority, which is a United Nations body. We'll go into that slide in a minute. This is the other type of deposit, marine polymetallic sulfides. These are called, the active ones are called black smokers, and they're interestingly, geologically, these are a direct analog of volcanic hosted massive sulfide deposits that are a common source of metals on mines and land. This is actually, when these were discovered, it's actually witnessing that type of ore deposit being formed. And they tend to be fairly small but very rich, 5% copper, 5 grams of gold, values like that, and in shallower water than the abyssal plains. Now these are the manganese nodules there. It's formed vast carpets on the abyssal plains. The challenge is mining at those depths. And the average grades are around 1.3% nickel, 1.1% copper, 0.2% cobalt. Those grades on land would be very rich. And there are estimated resources just in the Pacific alone is in the order of 270 million tons of nickel, be a similar amount of copper, 44 million tons of cobalt. That far outweighs, far greater than the resources known on land. So there's a huge resource available here. Now, the legal framework's interesting. The countries basically have the continental shelves around them belong to individual countries. Called the exclusive economic zones. That's up to 200 nautical miles, and it gives sovereign rights to petroleum, fishing, mineral resources, That can be extended in certain cases for the continental shelf, in some places is wider. So that's considered on a case-by-case basis. And then there is beyond that, there is the international seabed area. And I'll show you the next map, illustrates that. So the exclusive economic zones are shown in blue, 200 nautical miles around the countries. But in the middle, the open oceans is the international seabed area, known as the area. And that's administered by the International Seabed Authority, which is a United Nations body based in Jamaica, in Kingston, Jamaica. And anybody, any country, any government, or any company with the backing of a government is allowed to apply for concessions for exploration and eventual exploitation within the seabed area. So that means that it's an equitable way of sharing the mineral resources. Any country can participate in that, not just countries that border it, for example, or have a large area, or for example, landlocked countries can apply, or small nations can apply. So it's a form of administering as I say, the international common heritage of mankind for the benefit of all. Now this is the most recent map from the International Seabed Authority. They have 21 so-called contractors, so contractors being license holders, if you like, which can be governments or companies, holding 29 contracts of 15-year exploration contracts at present. The main interest is in the Clarion-Clipperton fracture zone in the Pacific. But as you can see, there are interests in Indian Ocean, Atlantic Ocean, Pacific, looking at different products. And there are 3 groups that I know of, there may be more, that are actually doing trial mining. JOGMEC is the Japanese government. They've already carried out trial mining for cobalt-rich crusts on a seamount. This is actually within Japan's economic zone, so it's Japan's own government that licenses this. And Japan, like Britain, is a small island nation and limited resources, so this will supply almost 100 years of Japan's cobalt needs and 12 years or more of its nickel needs. So Japan's going full speed ahead with that. This is the mining ship, or the research ship. And these things that look like bulldozers are undersea crawlers with cutters that will mine the material. The metals company is a company listed in Canada and on NASDAQ in the US. That's a commercial company associated with licenses with a couple of small island nations. This is their mining ship that's being fitted out in Amsterdam just now. The world's first subsea mining ship. You can see it's a big vessel. And the nodule collector on the warehouse on the left, so that will basically, a bit like a combine harvester, it will crawl along the seafloor collecting these nodules. They're carrying out pilot mining this year and hope to be in commercial production in a couple more years. And then the other one that's been active is the Global Sea Mineral Resources. That's basically the German government, their Geological Research Institute, the BGR, and the Belgian government. So 2 European countries looking at, again, in the Pacific for nodules and at a trial commercial stage. So deep sea mining is going to become a reality in the next 2 or 3 years, and that's going to be a very important source of, especially of battery metals. The oceans cover more than half of the Earth's surface, and they've not been considered up until now. So I've just about finished my time. I'll just draw some conclusions to the talk. So the energy transition, sometimes called net zero, sometimes called the EC's Green Deal, is going to need large amounts and increased amounts of many metals, more than actually produced just now, and most of them are critical raw materials. As we discussed, recycling has its limits. It can be improved, but it has its limits. Overall, there's no shortage of metals, but the challenge is discovery is getting harder, and it can take 20 years or more from exploration to production. So looking at a 30-year time frame for net zero it's difficult to see how the metals can be discovered and supplied in that time. New sources, I think there will be a return. Well, there is a return to domestic industry in the UK and the EU, partly motivated or partly incentivized by recent supply chain interruptions and cutting off of supplies of things like gas and wheat. Looking under deep cover, looking at new countries and belts, and finally, I think deep sea mining and deep sea minerals are going to be an important source of, especially battery metals. So that this is my vision for the future of mining in the energy transition. Thank you very much.
Well, thank you, Stuart. That is extremely interesting and extremely challenging, because it seems that the humans are caught in almost a cleft stick. It's on the one hand, the need to get all these various metals, including the rare earths, for these renewable energy developments and for cars. On the other hand, some huge challenges with discovery and mining. And I think, say, for example, deep sea mining, I could see all kinds of questions coming up, but it's open now to everybody. Feel free to unmute your microphones and let's see about questions. I can think of several coming to mind, but I'm looking around and I see several people here with the expression on their face of one who is about to ask a question.
Derek.
Stuart, I thought that was fantastic. I thought it was absolutely brilliant, really informative, totally interesting, hooked me all the way. Lots of questions in there. And Howie's bursting at the bit as well. And I think your primary premise, net zero, is only going to be accomplishable by offset. I just don't believe, like you, that there's going to be a net zero. So they're going to look at other methods to manufacture. And all the time, you've got commercial versus political. And politics is influenced by public opinion as well. And there's a move towards, environmental safeguards. And I think this is a massive clash.
Exactly, and that makes it even harder. Makes it longer to
absolutely
to build something or permit something. Yeah.
Well,
that's the great irony. Yeah.
That initial phase will be held up by litigation and all sorts of things. I'm just thinking, smokers. You're not going to touch the smokers. They're the only ecosystem on the planet that's not dependent upon the sun. That whole ecosystem is built on sulfur. And so that they are unique and rare. Well, they're unique. We don't know how rare they are, but they're unique in the world. So I think there's going to be a massive outcry if you go near there. And the whole point about getting the note. Sorry.
You would go for the fossil ones, the inactive ones, not the
right.
Not the active ones, obviously, in that case. Yeah.
And then you've got dredging. I know the abyssal plain is pretty low in biological productivity. But you're effectively doing the same as dredging. So there's going to be perceptual. Remember, it's all about perception.
Exactly. It's more like trawler netting.
Yeah.
Almost. Scraping the.
Well, that's right.
Scraping the bottom.
Along.
Yeah.
Yeah, absolutely. So there's
all
the
these things.
But
yeah, there's lots of questions. Yeah.
What about technologies just moving everything in a different direction? I mean, it seems to me, just from your talk, I'm thinking, forget electric cars. Absolute waste of time. Forget it.
Yeah, well, I think that's an important observation, yeah, and it's one of the, it's what conclusions are starting to lead to. And I think in terms of fuel generation, I think nuclear needs to make an important component of new supplies of electricity, replacing coal and so on as baseload. That's not fashionable. It's not, but it's one of the cleanest sources of energy.
And I promise this is my last question. He lied through his teeth. Where is the role for design in all of this? So that it's difficult within our systems that we produce now, cars and stuff, to recover these metals. What function does design going into the future have so that we build things that makes recovery of metals far easier?
Yeah, that's a good point. Yeah, to design things so that metals are more easy to recover. As I said, a lot of metals, for example, zinc, as a galvanizing coating, it tends to oxidize and will get lost. A lot of iron rusts away or gets lost in concrete. A lot of stuff gets disseminated in millions of small objects like cell phones that are hard to recycle or don't get recycled, often end up in the back of the cupboard. It's a good point, but I don't have an answer to that.
I think Bill, and this is one for Bill Graham in Forres. Bill, I know this is a subject that you've thought about very much.
It's things coming in from the side. I thought that was an interesting question, Derek, because we all extrapolate into the future, and there's these things come along that catch us by surprise. And you mentioned the amount of copper that's used in cars for electric motors, electric cars. Apart from the lithium, there's going to be a huge demand for copper. But it might be that electric cars don't take off at all, because I understand that it is actually possible to combine carbon dioxide with hydrogen from electrolysis from wind turbines to produce liquid fuels like methanol.
Yeah.
And they need catalysts too. And one that you haven't mentioned, I think it's rubidium that they found works in this process. And that might be one of the things that comes in from the side. And I'm sure there are others that we haven't thought about. But how is somebody keeping a watch on what might be a shocker?
Well, there's, for example, in battery technology, there's lots of other types of batteries being experimented with that don't involve lithium and cobalt. Things like sodium. I'm no expert on them, but or vanadium. Some surprises in technology could come from those areas as well, and revolutionize battery technology and storage technology.
So there are various areas being looked at, but I wonder if governments tend to look at a wider picture to see if they can pick up things like liquid fuels from carbon dioxide. It's recycling it. Seems like a good idea. It seems like it can be done. And there's a guy called Professor Ola who wrote a book called The Methanol Economy. So nothing's new about it, but you hardly ever hear liquid fuels being discussed and what catalysts they might need.
No, and with
I'm not sure why governments don't seem to have longer term view as something that's really important.
Yeah, and with that you could probably convert existing engines to use it rather than having to build
absolutely
completely new,
even use the same fuel tankers,
vehicles from scratch. Yeah,
absolutely.
Methanol was used and maybe still is used for racing cars.
But they did that in Bolivia
for engines.
Yeah, they did that in Bolivia, for example. They found large amounts of natural gas and converted most of the taxis and cars from petrol driven to gas. So they end up with a Calor gas tank in the boot, and they converted the carburetors and so on a bit, and the same vehicles running on a different fuel.
And LPG.
Taking advantage of a domestic supply, so it's cheap as chips. Yeah.
Can I jump in based on what Bill said? Your distribution of minerals and how that is held geopolitically. To what degree do you think minerals will become a ransom strip, which will force other governments to invest heavily in alternative technologies to reduce that ransom factor?
Well,
Think in particular of America.
Yeah, and already, for example, rare earths are basically monopolized by China.
Yeah.
And they've openly stated that they're prepared to use that to ransom or to hold back other countries. So that you need to develop other sources of those so that you're not at the mercy if they decide to turn off the supply one day.
Or other technologies rather than sources of the minerals, other technologies which don't rely on it.
Yeah, rare earths are used in so many things these days. That's the high-tech applications in small amounts, but have a wide variety of uses. But it's a fair point. When people are designing these things, nobody thinks about the supply of it. Okay, this dysprosium, we'll use it in this, but without any thought to supply. Although an interesting thing is that car makers like Tesla and some of the big ones, they're now making direct deals with mining companies to secure supply of things like cobalt and nickel, and in some cases rare earths, rather than because they're very concerned about secure supplies of metals, and they're even cutting back production because they can't guarantee metals or semiconductor chips and things like that. So it's an issue. Yeah.
What would their plan B be then? Presumably everybody has a plan B. I think that's the biggest snag that we have, is there doesn't seem to be a longer view on these things. I mean, you've presented it beautifully. It's pretty obvious we're running out of this stuff, and we're not thinking far enough ahead to do something about it.
No, I think the makers of technology, Tesla and so on, they come up with wonderful technology, but don't you can't just, they don't consider the supply of it. Now they're starting to realize that, because there's not enough supply. But I think when things started, we'll make all these batteries, but where do you get the metals from?
But that's because the argument is driven by economics, not by the Brundtland Commission wise use of resources, which do not inhibit future generations to make decisions. And we're discussing today finite resources.
Yeah.
There's supposed to be infinite resources in the sea, I've heard it said. I'm not sure exactly why it should be infinite, but I understand that it's possible to extract uranium from seawater. There's an organization in America who have produced what they call yellow cake by some filtering process using fibers in the water. And this, whatever happens, the yellow cake is formed on these fibers, and they can extract uranium from that. Is it possible there's a whole lot of metals dissolved in seawater, and with processes, many as yet not investigated, but which might yield a solution to a lot of these shortages?
There are, yeah. And there are a lot of, even in rocks as well, there are a lot of metals. There's no real, most metals there's no real shortages, but it comes back to economics, what you can extract at an economic. For example, in the days of the Soviet Union, they were short of bauxite raw material to make aluminium. That's almost all aluminium comes from bauxite, which forms in tropical weathering from places like Jamaica. Obviously, the Soviet Union had very limited supplies or access. So what they did was they used alkaline rocks, igneous rocks that are rich in aluminium as an alternative source of raw material for alumina. So when needs must, there are alternatives. Obviously, in the Soviet Union, economics wasn't a factor; it was more politics and requirements that drove technology rather than economic. But so other minerals can be extracted from other sources, including seawater. They say there's vast amounts of gold in seawater. There might be one, I don't know what the level is, 1 part per trillion or 1 part per whatever's below a trillion or above a trillion. Infinitely small, but given the volume, it adds up. But to extract that would cost more to extract than it would be worth. That's the problem. Yeah. But in some cases where the metal is deemed necessary, then there could be a case for looking at alternative supplies.
Yeah, that's probably why uranium's been picked for this attempt in the United States to get.
Yeah, I've heard of that, but there's not really, as far as I know, there's not really a shortage of uranium in rocks. There's plenty around, so I'm not sure why they would go to the trouble of extracting it from seawater.
Well, maybe they're looking ahead.
Well,
a lot of
maybe,
people are building reactors, aren't they? Pacific Northwest National Labs, that's where we're doing it.
Okay.
Bill, can I ask you just to expand a little bit on the methanol option, because it does seem indeed that by going down the fuel cell option with hydrogen or by battery cars, there comes this very difficult need for these various metals. But you're saying, in fact, that methanol is an alternative to use existing vehicles.
Yes, I am, because it will run in existing vehicles. We know that, as I said earlier, model aircraft have been flying for years with methanol as the fuel. And that's true of other alcohols that you might produce by the same method or similar method. It's the catalyst that's been the sticky bit. But hydrogen, it's been quoted as being the answer. I'm suggesting it's combined with carbon dioxide is a better answer, because hydrogen has the big snag that its energy density per unit volume is pretty low, really. So either you have to compress it or liquefy it, and that means weight. So for small vehicle transport, it's not terribly economic. It's okay for big things like buses on short distances, but for a car to carry hydrogen as a fuel for the distances that we're expecting from electric vehicles is really quite difficult. Hydrogen, it's got a lot of energy in it, and it gives water out when you burn it, and it does work in fuel cells, but it has this transportability problem, which is also true of supplying it to households for central heating, where they're talking about and are running in local areas tests with 10% hydrogen in natural gas. But to replace the whole of it means that the gas grid will not be capable of handling the volume of gas that has to be passed through it. And also, if they increase the pressure, they're quite likely to lose quite a lot of it, because hydrogen tends to get out fairly easily. So you've got to think about the whole problem again. It's the wideness of trying to look at it that's difficult. Yeah. And it's the bits that come out of the side that hopefully bring the really good surprises.
Yeah.
I've got my fingers crossed for methanol, and I'm hanging on to my old car with a petrol engine.
Yeah. For the day you can convert it. Yeah.
Did they not use it in Brazil? Did they not have methanol cars in Brazil?
Yeah, they use
gas. Well have done.
Yeah, they call it gasohol.
The Indianapolis races in America for years
are
on methanol.
Yeah, in Brazil they use it. They make it from its bioethanol. I think it's ethanol, not methanol. From cane. They have vast cane fields. So you go around the city, the air smells sweet from the fumes of alcohol. They call it gasohol, gas alcohol.
A pleasant side effect.
Yeah.
It has the added advantage that you can easily find people who've been siphoning your fuel tanks.
Yeah. Yeah.
There's time for a couple more questions, if anyone would like to ask a couple more.
Yeah, one thing that puzzled me when you were speaking earlier was, I think it was Stuart who said it, it's not really possible to recover these materials from the things that we throw away, like mobile phones. And design came into it. There is a bloke I know who's got a phone which is actually assembled from bits. So it all plugs together in different ways and they'll have different functions. And you can send them back if it fails and get a replacement component. But the components themselves are being broken down, as I understand it. And also from the material itself, you mentioned solder, but is it not possible to just smash it all up and heat it until the solder runs out? I know gold might be a bit harder, but solder I would have thought might be possible. So
Yeah,
presumably somebody's looking at all this.
I think yes, you can recycle them. The problem is more that collecting them to recycle them, you end up with billions of small units spread over the whole world, and what percentage of those actually get handed into recycling or collected for recycling? I think you can melt the thing down and get the metals out, and that's done. But I think that it's more a question of gathering them all together.
Yeah, we could do a lot more about collection. It's really poor, particularly plastics, I think. I mean, we don't even stamp everything with the identification logos, the little triangle with a number in it. The amount of stuff that comes to our bin, and I just say it must be PET and chuck it in the PET bin, you know. But we should be doing that. How long has that code been in place? And we should be collecting them according to the numbers on them.
You're quite right, Bill. It's quite extraordinary. I just read in the newspaper yesterday, apparently to buy a bottle for a brewery, to buy a bottle to produce beer, they have to pay about 60 pence. And that's absolutely extraordinary, because then we buy the beer and then there's no system for us to get the beer bottle back to the company. And you'd surely think if it's 60 pence to a new one, it would be much, much cheaper for the company to have a simple system to give us even 10 pence. So I think systems, it just seems we are extraordinary poor at having simple, because I do remember as a kid collecting lemonade bottles at dances.
Exactly.
And actually as a student, when our digs, I remember, we ran dry and we managed to fill a huge rugby bag full of empty bottles and had enough for another night. And it was such a simple system. You know, anybody who sold, basically anybody who sold things in bottles took them back again. And I can't understand how it's so difficult to do that today.
Yeah, we used to do that as well.
Howie,
collect old bottles.
Howie, you're missing something there, which is bureaucracy, and we're completely tied up in that. As a beekeeper, I've only just learned, having had to buy a whole lot of honey jars, that it's illegal to sell honey in a jar that isn't new. So it is actually illegal. So, you know, let's get a perspective here. We're doing things that are completely daft in many ways. I've got a lot more to say on that sort of thing, but there you just made me say that. Yeah.
Ulrich, what an excellent point.
Do you remember the point that I made? That is where our arguments are centered. Everything is centered on the economic or the bureaucratic thing. I remember Tomorrow's World in the 1970s. There were German houses where the person was at the sink, and in front of them was a whole series of sort of letterboxes, large letterboxes, where you did the recycling and you put the stuff in. So a part of the cost would be offset by the fact that if they built systems that were easy to take apart, like your phone bill, and we have receptacles where we do the sorting.
Yeah,
and it's where we're centered. We should be centering on quality of life for people and how we move forward and use our resources wisely. And it's not, it's centered by economic and political drive.
Derek, you're the real heretic. We must get together and talk more.
I'll bring the wine, you bring the honey.
Harry's got plenty of bottles left over from.
That's right.
A lot of bottles. This has been a super session, a super discussion, and absolutely fascinating, Stuart. You know, I'd come across this topic just occasionally in the newspapers with a brief mention, but tonight you've really given us a systematic and very clear analysis of the problem, and actually shown ways in which it can be approached. So thank you very much indeed. And yes, I think we definitely should.
Yeah, no, absolutely fabulous.
A round of applause. And
Thank
Stuart,
you.
doing it from Panama as well, I think that is tremendous. Now, we'll be meeting again in a month's time, which will be the last Wednesday in June. And we've actually got a gap because I think we haven't at the moment got a paper for it. I will check and see. But if we haven't for any reason, if any of the audience here today has got a topic that they would like to bring up, this would be a super opportunity to do it, whether to recommend it or to prepare it yourselves. Some really interesting points have come up tonight, I think, about design, for instance, and about having a total picture, a total integrated view of energy and minerals and much else. And all that remains for me to do is to thank our speaker, Stuart, again. And nice comments just come in from Leslie and Orkney. A fascinating talk. Many thanks.
Thank you.
Well said indeed.
Thank you.
Yeah.
So
Brilliant.
we'll look forward to meeting up again in a month's time. And in the meantime, thank you all.
Vote of thanks to the chair.
It was a pleasure.
Bye.
Thank you.
Cheers to everyone.
Cheers, everyone. Thank you.
Bye, everybody. Bye.
Bye.